I'm going. I'm going to continue with doing problems from the back of the book. Right now, I'm on problem 64. So let's take a look at 64. Need to grab my book just in case I need it. Okay, the enthalpy change for the oxidation of styrene, C8H8, is measured by calorimetry. So here we have styrene reacting with 10 oxygens to give you 8 carbon dioxides and 4 H2O. This is your typical combustion reaction of a hydrocarbon. They say that the enthalpy of reaction, the standard enthalpy of reaction, that's what that little circle at the top means, standard, is minus 4,395.0 kilojoules per mole of reaction. Use this value along with the standard enthalpies of formation of CO2 and H2O to calculate the enthalpy of formation of styrene in kilojoules per mole. So what they're asking us to use is this particular equation. The enthalpy of formation reaction, the enthalpy of the standard enthalpy of reaction is equal to the sum of the enthalpies of formation of the products, sum of the enthalpies of formation of the products, standard enthalpy of formation, minus the sum of the standard enthalpy of formation of the reactants. So if we kind of fill in what we have here with these different ideas, you can see that this standard enthalpy of reaction is this value here, but I don't want to plug numbers in quite yet. I'm not ready for that. So what I'm going to do is I'm going to first start with the standard enthalpies of formation of the products. You'll notice we have CO2 gas. So to get the standard enthalpy of formation of these products, we want to do this per mole of reaction. So in general, we're just going to take 8 times the standard enthalpy of formation of CO2 gas. Now, why are we using 8? Because there are 8 moles of CO2 here. And then plus 4 times the enthalpy of formation of H2O liquid. Okay, so that is the sum of the enthalpies of formation of the products. Minus, here we have 1C8H8 liquid, and here we have 10 enthalpies of formation. And I forgot to write enthalpy of formation here. For oxygen gas. Okay, so here they want us to calculate the enthalpy of formation of styrene, which is this value right here, based on all of these other values. So I'm going to do my little algebra magic, and this change in enthalpy of formation of styrene is going to equal I'm going to go ahead and put a negative here, a negative here, a negative here, and a positive here so that that becomes positive and that becomes positive. So basically I took the negative of everything. So the enthalpy of formation of styrene is going to be, when I take these over to this side, 8 times the enthalpy of formation of CO2 plus 4 times the enthalpy of formation H2O liquid. And when I take this to the other side, it's going to be negative 10 enthalpy of formation. I forgot my H here. Of O2. And then minus the heat of reaction. Okay. So let's plug these values in. What is the standard enthalpy of formation of CO2? Well, we have to look it up in our book. So it's in Appendix L, I believe. And on an exam, we would not be giving you an appendix to look things up. We just give you the values. Because the tough part is not looking up the values, it's actually doing the problem. So for carbon dioxide, I see that the enthalpy of reaction for the gas is minus 393.509 kilojoules per mole. So I have 8 times negative 393.509 kilojoules per mole. And for H2O liquid, we have 4 times negative 200, and I want to say 40 something. Note for the liquid, it's minus 285.83 kilojoules per mole. And what about the enthalpy of formation of oxygen? Well, the enthalpy of formation of any element in its standard state is 0. So we're going to have negative 10 times 0 kilojoules per mole. And then minus the enthalpy of the reaction, which is minus, so this is minus a minus, negative 4395.0 kilojoules per mole. Okay, so now it's time to take out the old calculator and get the answer. But first I'm going to estimate it. This is 400 times 8, which is, let's see, 4 times 8 is 32, isn't it? Let me think about that. Yeah, 32. So this is negative 3,200. I'm going to write that right here in small numbers. That's 300 times 4. So 300 times 4 is negative 1,200. That's 0. And that's, I'm going to call it negative 4,400. Now I can see that this negative 1,200 is a little bit over because these are 2815. So this should probably be more like a 1140. And here, this is like 7 over. 7 times 8 is almost 50. So this should be more like 3150. Okay, so when I add all of these numbers up together, you can see I'm going to get from these two numbers basically minus 4,300. And added to that, I get minus 8,700. So let's see what we get. 8 times negative, well, I'm going to just do this. Oh, I made a mistake. This is negative, but a negative of a negative makes that a positive. So that means the answer is going to be about positive 100 because these add up to 4,300. Okay, so 8 times 393.509 plus 4 times 285.83 and then minus 43.95.0. Oops, I made some sort of mistake. I see what it is, 4395.0. Okay, I get minus 211 or positive 211.6 kilojoules per mole. I must have estimated incorrectly or used my calculator incorrectly. So I'm just going to double check on the calculator. 8 times 393.50 is actually 3148. And 285.83 times 4 is actually 1,143. And when we add these all up together, so 3148 and then I subtract 4395.0 Uh, so this time I get negative 104 kilojoules per mole. Now, when we're trying to keep track of significant figures, you can see that when we add these numbers together, this is going to be good to the 10th. When we do 4 times 285.83, that's actually going to be 1143.3. It's good to there. And when we do 8 times 393.509, this is going to be good for 6 significant figures. So 4314807, that's good to there. So when we add these all up together, we're actually going to be good to the 10th. So I need another digit here, and let's see what that is. Oh, and this should be a positive. So I actually get minus or positive 103.6 kilojoules per mole with the correct number of significant figures. So that's how you do a problem like that. It all starts with this equation right here, and understanding that when you do the enthalpy of formation of the products, you have to take into account the moles of reactants and products. Okay, so let's put that one off to the side. I'm kind of looking in the book to see if they have the value for styrene, and they don't. Okay, so that goes off to the side, and this goes off to the side. So let's take a look at these next problems. So we have A through D. For each of the following, tell whether the process is exothermic or endothermic. Now, I want to remind you that endothermic means that energy is absorbed. The delta H is positive. What else can we say about endothermic? I think that pretty much captures it. And exothermic, oh, I thought of one more thing. Heat is a reactant. So here, energy is released. Delta H is negative, and heat is a product. So we can keep these things in mind when we assign whether or not these things are endothermic or exothermic. So we have H2O liquid turning into H2O solid. Now, the way I like to take a look at this one is using the idea of change of state, because we have liquid going into solid. And this is the way I always like to draw it. This is the solid. This is the liquid. And this is the gas. And the reason I draw them this way is because this is really a potential energy diagram. Here you have high PE, and here you have low PE. The arrow points in the direction of the higher amount. So gas, H2O gas has more potential energy than H2O liquid, and H2O solid has less potential energy than H2O liquid. So as you go through these changes of state, you get higher potential energy, and that's why we take water and turn it into steam to run turbines so that we can generate electricity. Okay, so lower potential energy, higher potential energy. How do you get something to have higher potential energy? You have to put energy in, which is endothermic. So in that direction is endothermic. So what does the opposite direction mean? It means exothermic. So if we take a look here, we're going from a liquid to a solid. This is going to be exothermic. Okay, so you might be thinking, but when I freeze water, I have to stick it in a freezer, which is cold. Yes, you do. The freezer is cold, but why is the freezer cold? And the answer is because your refrigerator has pulled the heat away from the freezer. So heat is leaving the freezer. Heat is a product from the freezer. It's exothermic. Okay, let's take a look at B, where we have H2 gas plus O2 gas gives you 2H2O gas. This is a reaction where if you take hydrogen and react it with oxygen, it blows up. So a lot of energy is released, and so this is going to be exothermic. What about the next one where you have H2O liquid at 25 degrees Celsius turning into H2O liquid at 15 degrees Celsius? Well, we know that if it's 15 degrees Celsius, we're going to have to put energy into it to get it to be 25 degrees Celsius. So that's endo. So the opposite is exo, and they actually ask us for the opposite, going from 25 to 15. So that's exothermic. So in order for us to cool down that 25-degree water, we have to make heat leave it, and heat being leaving it is basically heat as a product. C, H2O liquid turning into H2O gas. Well, for this one, when you have the liquid turn into the gas, that's definitely endothermic. Okay, so we're done with that one. What does the form standard state mean? And the answer is really simple. Standard state means the following. Move this just a little bit. Standard state means the state, the physical state, solid, liquid, or gas, under standard conditions. State of a substance, solid, liquid, or gas, at standard state conditions. Now, that answer is not enough because we're saying the state of a substance at the standard state. Oh, okay. What do we mean by standard state? That is 25 degrees Celsius. It's defined, so that's exact. And 1 atmosphere of pressure. And that's also defined, and that's exact. So basically, room pressure or room temperature under normal pressure. Okay, so what are the standard states of the following? So notice they have 295 K, should be really 295.15 K. So H2O, I think we know, is a liquid. NaCl, which is table salt, we know is a solid. Mercury, most of us know, is a liquid at room temp. It's one of 2 elements that are a liquid at room temp. The other one is bromine. And CH4, now if we know the name of this, methane, we probably have an idea of the standard state, and that's a gas. Small molecules are often gases at room temperature, which is really surprising for H2O because it's a molecule and it's a liquid at room temp. So water has some fantastic properties that are not normal. Okay. Now, something that's not asked is, what is the standard state reaction for each of these? So the way to do that is you start off with the product in its standard state. And then once you have the product in its standard state, you look at the elements in here. There's hydrogen and there's oxygen. And then you have to write these in their standard state. So these are both Hunkelbriefs, so you put 2. They're both gases at room temperature, so you put gases. And then to balance this reaction, we have to put coefficients in front of these guys because the standard state reaction is always exactly 1 mole of product. So we can't change the coefficient here. 2 hydrogens and 2 hydrogens, 2 oxygens and 1 oxygen, we have to put a 1/2 here. So this is the standard state reaction for H2O liquid. So what would it be for NaCl? Well, we start off with NaCl solid. The two elements that make up NaCl are Na and Cl. Cl is a Hunkelbreath. Cl is a gas at room temperature. Sodium is a solid at room temperature. There's only one metal that's a liquid at room temp, mercury. And to balance this, you can see we need a 1/2 in front of the Cl2. How about mercury? What is the standard state reaction for that? Well, we start off with mercury liquid. And what are the elements? Well, there's mercury. What is it? Is it a Hunkelbreath? No. What's its standard state at room temp? It's a liquid. And then we have one mercury turning into one mercury. This, we know that the enthalpy of formation reaction is 0 because it takes no energy to take a mole of liquid mercury and turn it into a mole of liquid mercury at its standard state. And for CH4, we've got carbon plus hydrogen. Hydrogen is a Hunkelbreath and a gas. Carbon is a solid, and we put a 2 there. And these are all the standard enthalpy reactions for each of these. Okay, let's put that to the side. Okay, you have a large balloon containing 1 mole of gaseous water vapor at 100 degrees Celsius. How will each step affect the internal energy of the system? So when we talk about the internal energy of the system, this is this delta U, if you will, which is going to equal the Q plus the work. Okay, so let's take a look at the steps here. You have a large balloon containing 1, and for this balloon, we're going to assume that the balloon is flexible, it's easy to expand or contract, so it's more like a large bag containing 1 mole of gaseous water vapor at 80 degrees Celsius. Okay, so for step A, what's going to happen when you raise the temp? Well, when you raise the temp, you're going to increase the heat, which means you're going to increase the internal energy. B, the vapor is condensed to a liquid. So that means that the H2O gas is going to turn into H2O liquid. And we know that this happens to be exothermic, right? And how do we know that? Well, because we know that if we take the liquid and turn it into the gas, that's endothermic. So the opposite would be we're going to lower the potential energy. But there's something else that we need to think about. What is work made out of? Work is equal to the pressure times the change in volume. So in a system like this, the pressure stays the same, but the volume will also decrease when we turn this gas into a liquid. So here, and actually this is the work is negative P delta V. So here, change in volume decreases, right? And times the pressure, which also stays the same. So what happens here is that the work is done on the balloon to compress it. So what do we mean by that? Well, if work is done by the balloon, that means the work is going out. And if work is done on, work is going in. So it's kind of like endo and exothermic. So work is being done on the balloon, which means that the energy is decreasing, if you will. So overall, when this is exothermic and this is decreasing, the change in internal energy should go down. Now, I'm going to be honest with you. If you're listening to this, I don't ask you for a whole lot of questions on the exam or the quiz about changes in internal energy based on gases or things like that. I will ask you for change in internal energy for a constant volume calorimeter. And I like to just call that change in enthalpy because that's pretty much what it is. Okay. Now here, Determine whether energy as heat is evolved or required, and whether work was done on the system or whether the system does work on the surroundings in the following processes at constant pressure. So if we take a look at A, we have ozone decomposes to form O2. So ozone is a gas. It decomposes to form O2. And we want to go ahead and balance this reaction. So we're going to put a 2 here and a 3 here. Okay. We want to know whether work was done on the system or the system does work on the surroundings. This really is a matter for another chapter because it talks about gases. And so the deal is that when you have 2 particles of gas decompose into 3 particles of gas, what happens is it takes up more space. So here, the amount of space particles takes up at constant pressure depends on how many particles you have. So if we go from 2 particles to 3 particles, it's going to take up a little more space. How much more? By 1/2. So we take 1/2 of this and add it to it, and that's how much more space it takes up. Considering that, I should probably draw this way because this looks like 1.5 times bigger than that. Okay, so was work done on the system, or does the system do work on the surroundings? And a very convenient way to think about this is this way. Imagine you have a plastic bag and you put CO2 solid in there and you have a book on top. Okay, so when that CO2 solid turns into a gas, the bag plumps up because you have CO2 gas. Well, what happens to the book? The book rises in level. So this is work done on surroundings. Now, what if it were the opposite direction? This would be work done on the system. Okay, so here, what do we have? Do we have the bag getting larger, or do we have the bag getting smaller? Looks like we have the bag getting larger, so this is work done on the surroundings. Now, again, I'm not going to be asking you questions about work on the exam, but it's kind of interesting to see this. Now, what about the heat for this? Is there any heat associated with this? We don't really see any heat being done on this. There's no mention of heat, so we're going to assume that there's no heat change per se. Now for B, we have CH4 plus 2O2 turning into CO2 plus 2H2O liquid. So we have a couple things going on here. Now, one of the things is that you'll notice we have 1, 2, 3 moles of gas turning into 1 mole of gas. So here's your 3 moles of gas turning into the equivalent of 1 mole of gas. So this is supposed to be 1/3 the size of this. So if we look at this, this looks like the balloon getting smaller, the balloon getting smaller. So this means work is done on the system. So that means energy is going into the system. But on the other hand, when we take a look at this is a reaction that gives off energy. It has heat as a product. So heat as a product means that this releases energy. And then furthermore, we have gases that are condensing into liquids. And that's also exothermic. So it looks like we have a couple of exothermic things and one endothermic thing because work is done on the system. So overall, it's probably a good bet that this is the winner. And overall, it's exothermic. And the change in internal energy decreases. So these are some tough things that they're asking us about. But again, I usually don't ask about these on the exam, but they're interesting to talk about. Okay. Which evolves more energy on cooling from 50 degrees Celsius to 10 degrees Celsius? So this is one of those ones that we simply use the specific heat capacity. So specific heat capacity, or Q, is equal to specific heat capacity mass delta T. So we want to calculate which one evolves more energy. So evolves should mean that energy is released. And therefore it should be a negative value. Okay, so let's look at ethanol first. So here we have that the amount of energy evolved is going to be the specific heat capacity of ethanol. So 2.46 joules per gram degrees Celsius. And I want you to recall, I said for specific heat capacities, we can use degrees Celsius instead of K anytime we want. And you don't have to do any conversions. Okay, so that's specific heat capacity. The mass of the ethanol is 100 point grams. And the change in temp of the ethanol is going to be the final temp minus the initial temp. So the final temp is 10 degrees Celsius. And I'm going to put a little dot there and a little dot there. So we have two zig figs there. Okay, so let's estimate the answer. Negative 40 times 2.46 should be roughly negative 100. Negative 100 times 100 should be 10,000, something like that. And we get two significant figures, it looks like, because this 50 minus 10 is 40, but that's of course a negative 40 because that's negative 50 and plus 10. And we round to the ones. So let's see what we get here. 2.46 times 100 times 40, and we get 9840 joules. Now, when I round that, we get 9800 joules because we're only allowed two significant figures, so we'll keep the 9 and the 8. And the 4 turns into a 0. Remember, trailing zeros don't count unless you have a decimal. Now, let's look at the water. Now, for the water, we have Q is equal to, now, normally we like to use 1 calorie per gram degree Celsius because the specific heat capacity of water is defined as being 1 calorie per degree Celsius. But we also know that 1 calorie is 4.184 joules per gram degree Celsius. So it's okay to memorize this one. Now, notice we only have 50 grams of water. And we still have the same temperature change, 10 degrees Celsius to 50 degrees Celsius. Or I should say 50 degrees Celsius to 10 degrees Celsius. We always start with the final temp. So here I have negative 40 times 50, which sounds like 2,000, right? 2,000 times 4 should give me around 8,000. So let's see what we'll get. 4.184 times 50 times 40. And I get, again, two significant figures, so I'm going to round right away. 8,400 joules. Okay, now these should both be negative values because of the negative here, negative 40. So, which evolves more energy upon cooling? The ethanol evolves more energy according to our calculations. Okay, I'm going to pause this for just a moment. Okay, so we're done with this problem here. I'm going to put this over here, and I'm going to take this and put it over here. So here we have calculate the quantity of energy required to convert 60.1 grams of H2O at 0 degrees Celsius to H2O gas at 100 degrees Celsius. They give us the enthalpy of fusion of ice is at 0 degrees Celsius is 333 joules per gram. And the enthalpy of vaporization of liquid water at 100 degrees Celsius is 2,256 joules per gram. So if I draw a little diagram over here of what's happening without regard to scale, we're going to start at 0 and we're going to end at 100 degrees Celsius. Now, this is with 60 grams of water. If you start at 0 degrees Celsius and it's ice, all of the energy goes into melting the ice. After all of the ice is melted, the liquid water that's formed will then rise in temperature until it gets to 100 degrees Celsius. Once all of the water is at 100 degrees Celsius, all of the energy goes into turning the ice or the water into steam. So this is vaporizing or boiling, I like to say. And this is heating water. So that's what's going on. So we can look at each of these situations in turn, A, B, and C. So let's look first at A, where we are melting 60.1 grams of H2O solid. Now, for any change in state, to calculate the Q, you do the heat times the mass. And so heat of what? Well, in the case of melting, it's called heat of fusion. So we're going to have 333 joules per gram times 60.1 grams. And the way I kind of look at this is that it's almost like that's 1/3. I know it's not 1/3, it's 333, but I like to put the decimal there and think, oh, 1/3. 1/3 of 60 is 20. But then I think, okay, so the answer is 20, but 20 what? Since I have 333 times 60, I know the answer is going to be bigger than 3,330 because times 10 would be 3,330. So I'm thinking that it's going to be closer to, say, 20,000. So let's see what we get. 333 times 60.1, and we get 20. We only get 3 significant figures, so 2, 0, 0, 0, 0 joules. So I need to write this as 2.00 times 10 to the 1, 2, 3, 4 joules. So I have 3 zig figs. So that's A, the melting. Now we have to give the sign here. We are taking ice and we're turning it into water. So that means we have to put energy in. So this is definitely a positive. So whenever you're doing a heat calculation for a change in phase, you have to understand that you have to add the sign to that energy. And when you're putting energy in, it's positive. When energy is being released, it's negative. Now, if we take a look at B, for the water heating from 0 degrees Celsius to 100 degrees Celsius, we're going to use the specific heat capacity of water. So Q equals 4.184 joules per gram degrees Celsius. The mass of water is 60.1 grams. And the change in temperature is going to be 100.0 degrees Celsius minus 0.0 degrees Celsius, which is 100 degrees Celsius. So 60 times 4 is roughly 240. 240 times 100 is what? 240, 24,000, 24,000. So let's see what we get. And it's going to be a positive value because here it's a positive value. So 100 times 60.1 times 4.184, and I get 2.51 times 10 to the fourth joules. And again, three significant figures. And for C, we're going to use the heat of vaporization. So we get Q is equal to 2256 joules per gram times 60.1 grams. So this is kind of a hard one to estimate, but you can tell it's going to be clearly 22560 and then times 6. So it's going to be, oh my goodness, 120,000, 130,000. 2256 times 60.1, and I get 1.36 times 10 to the 5 joules. Okay, so we have to add these three values together to get our total amount of energy, because they don't want the energy for each of these, they want the total. So when we add the total together, A plus B plus C, the 6 here is the least precise place out of all of these compared to the 1 or that 0. So we're going to round to there. Let's see what we get. Plus 2.51 second EE4 plus 2 second EE4. And we get 1.81 times 10 to the 5th joules. So if I kind of line these up to add them together, I get like 136,000. So 1, 2, 3, 4, 5. This would be 20000, and this would be 25100. So when you add these together, you get the following. 5, 8. So that's why it seems like we should get that plus that is around 5, or 4, plus that is around 6. We should get around 6, but remember, these are times 10 to the 4th. They're very much smaller. So that's how you do this problem. Okay, so let's move on. I'm hoping to get to some really good stuff here in a little bit. Please refer to the book, blah, blah. Okay, chloromethane, a compound found throughout the environment, is formed in the reaction of chlorine atoms with methane. Okay, so calculate the enthalpy change for the reaction of CH4 gas and Cl atoms to give chloromethane and hydrochloric acid. Is the reaction exothermic or endothermic? So I imagine that they want us to use that equation where we have that the enthalpy of reaction is equal to the sum of the enthalpies of formations of the products minus the sum of the enthalpies of formations of the reactants. So we're going to say that this is going to be the sum of, here we have 1 chloromethane. So I'm going to put 1 times the change in enthalpy of formation of chloromethane gas, the state matters, plus 1 times the change in enthalpy of formation of HCl gas, minus the sum of the product or the reactants. 1 times the enthalpy of formation of CH4 gas, and plus 2 times the enthalpy of formation of Cl gas atom. Okay, so let's look these up in our book. So CHCl3, Cl gas. There it is. So this is going to be 1 times negative 103.18 kilojoules per mole plus 1 times for HCl where is HCl? Oh, there it is. They put it under with chlorine. So minus 92.31 kilojoules per mole minus CH4. So CH4 is 1 times negative 74.87 kilojoules per mole. And then plus 2 times, let's see what Cl is. It's 121.3 kilojoules per mole, and it is a positive value. So we're going to add these all together. We can see that's negative 100. That's negative 92. We add these two together, we get negative 195. Negative 195 in here, negative of a negative is a positive. So when we add this to our negative 195, we only have negative 120 afterwards. So negative 120, and then we have a negative of a negative here. So negative 120, and 2 more 120s puts this at about 360 for our answer. So let's see what we get. Negative 103.18 plus a negative 92.31, and then minus a negative 74.87, and then minus a 2 times 121.3. So I'm going to call that 242.6. And I get minus 363.22 kilojoules per mole. Now, where do we round to? Well, 1 times this is good to the 100th. 1 times this is good to the 100th. 1 times this is good to the 100th. 2 times this is going to be good to the 10th because we get 242.6. So we round this to the 10th. So we get negative 363.2 kilojoules per mole. And that is the enthalpy of this reaction. Okay, is the reaction endothermic or exothermic? It is exothermic. Why? Because the sign is negative. Okay. Draw an energy level diagram that shows how the various enthalpies in this problem are related. So they're talking about, actually, they're talking about a pretty complex problem. Let me show you how to do it. This is a problem that is more complex than what you're going to have to do on the exam, but you're going to have to do it on the exam nonetheless. Okay, so we have that the reaction is CH4 plus 2Cl gives you CH4Cl gas plus HCl gas. And we used enthalpies of formation for each of these. So let's write out the enthalpy of formation reaction for each of these. So for CH4 gas, it's made from carbon and hydrogen. Hydrogen is a Hunkelbrief, and it's a gas at room temp. Carbon is a solid at room temp. And to balance this, I put a 2 here. And the energy for this one is negative 103.18 kilojoules. Okay, so we need to do that for all of these. So the next one I'm going to put is Cl gas, and the enthalpy of formation for this one was 121.3 kilojoules. And here I'm leaving the per mole off. That's fine. Here, we're going to make exactly 1 mole of that. It's made from chlorine, which is a Hunkelbrief and a gas at room temp. And to make it balance, I have to put a 1/2 there. Okay, next we have CH3Cl. So the change in enthalpy of formation for this reaction is going to be, let's see, CH3Cl. Oh, I gave this one the wrong value. This one is actually minus 74.87. This one is minus 103.18 kilojoules. So here we've got the CH3Cl gas, and it's made from carbon, hydrogen, and chlorine. Chlorine's a Hunkelbrief, hydrogen's a Hunkelbrief, and carbon is not. Carbon is a solid at room temp, hydrogen is a gas at room temp, and chlorine is a gas at room temp. Now to balance this, I have to put a 1/2 in front of Cl2. Let's see, I need 3 hydrogens, so I'm going to put 3/2 times the hydrogen and 1 carbon. So there's that reaction. And the last one, the enthalpy of formation for HCl is minus 92.31 kilojoules per mole. And for HCl, we're going to write HCl gas. And then we're going to write H and Cl. Cl's a Hunkelbrief and a gas at room temp. H is just a Hunkelbrief and a gas at room temp. Put a plus here, and I have to put 1/2 and 1/2. Okay, so I need to show how all of these reactions interrelate along with this reaction here. Now, one of the nice things about this is that we already have a balanced reaction. So that means I need to have in my overall addition 1 mole of CH4, 2 moles of Cl, 1 mole of CH3Cl, and 1 mole of HCl. So you can see that this reaction here, I need to double so I get 2 Cls. So to double it, 1/2 times 2 is 1. So I'm going to write Cl2 gas gives you 2 Cl gas. And the enthalpy of reaction here, I can't call it formation because I'm now making more than 1 mole of Cl, is going to be 42.6 kilojoules. Okay, so I want to show how these 4 reactions, this one, this one, this one, and this one, not this one because we had to double it because of that, how they're interrelated in an energy level diagram. So let me show you a very simple energy level diagram. So we're not ready for the big boys here yet. Let's do something simple. Okay, so here's the simple thing I'm going to show you. The enthalpy of formation of H2O liquid is as follows. H2 gas plus 1/2 O2 gas gives you H2O liquid. That's the enthalpy of formation reaction for 1 mole of water. And the change in enthalpy of formation for this is negative 285.83 kilojoules per mole of water formed, or per mole of reaction. Okay, now the enthalpy of formation reaction for steam is the following. And the enthalpy of formation reaction for this is minus 241.83 kilojoules per mole of reaction. Okay, so these are two reactions. First of all, I'm going to say that this one is exothermic, and this one is exothermic. So I want you to recall that when I was doing things like this, where we go from a solid to a liquid, this is endothermic, and the reverse is exothermic. And that kind of makes sense. You have to put energy in to get a solid to melt. And therefore, when the liquid freezes, it should release energy. Okay, so the key here is that we have an arrow down for an exothermic reaction and an arrow up for an endothermic reaction. So these can be thought of as reaction arrows. So I can take this S, which is at the bottom of this arrow, have the arrow lead to the L, and I know that this reaction is endothermic. Likewise, if I start at the L, which is at the bottom of this arrow, and go to the S, L to S, this is exothermic. So that's an important thing to remember. Arrow up is endo, arrow down is exo. Okay. Another thing that's important to remember is that when you draw your arrows, at this end, you draw your product, and at this end, you draw your reactant, regardless of how you position your arrow. So the arrow always points to product. So if I put an arrow like this, what am I going to put on this end? I'm going to put product. What am I going to put on this end? I'm going to put reactant. So no matter how you turn your arrow, that's what you always do. Okay, so let's combine these ideas. This is an exothermic reaction, so I'm going to draw an arrow that goes down. How big is this arrow? It's minus 285.83 kilojoules. In this reaction, what is the product that I'm going to put at this end of the arrow? It's H2O. Now, normally you do something like this and you draw a little line instead of drawing it at the end of the arrow. So what this says is this is the energy level right here of H2O liquid. Now, what do I draw at the other end of the arrow? So notice, instead of drawing it at the end of the arrow, I'm drawing a little line there. I have H2 gas plus 1/2 O2 gas gives me H2O liquid. And I've just drawn an energy level diagram for this very first reaction. So let's draw an energy level diagram for the second reaction. What does the negative mean? Exothermic. Is exothermic arrow up or arrow down? That's right, arrow down. Now look at this arrow compared to that one. I'm making that one shorter. Why? Well, because this arrow is 285 long, this was only 241 long. Now, I'm not trying to make this proportional. I'm trying to make it obvious that this arrow is smaller than that one. So here, what do I put at the pointy end of the arrow? The product, H2O gas. And what do I put at the other end? I put the reactants, H2 gas plus 1/2 O2 gas. Now, we're going to put these all together. Notice that this pair of reactants is exactly the same as this pair of reactants. And here we can actually connect that and say, oh, they're the same level. And here I can bring this over and we can see, oh, that's below that, right? So now let's take a look here. If we connect these two diagrams over here and I draw a little arrow up, this says that we have to put energy in to take H2O liquid and turn it into H2O gas. Does that make sense? Makes total sense. How much energy do we have to put in? We have to put in the difference between these two values, which is going to be 44.00 kilojoules. Now, if we turn the gas into a liquid, what's going to happen? Well, it's minus 44.00 kilojoules. Why is this up positive and why is this down negative? Well, because up is endothermic and down is exothermic. So we've just discovered the enthalpy of vaporization for liquid water based on enthalpies of formation of H2O liquid and H2O gas. So those are important things to remember. The arrow is the reaction arrow. The arrow points to the product. The arrow goes up if it's endothermic and down if it's exothermic. Okay, so now we're ready to give this a try. Now, when you're giving this a try, where do I normally start? And I want you to remember, we also have one more reaction here, and that reaction is the following. So I need to move my papers around a bit. The other reaction we have to write is this one right here, CH4 gas plus 2Cl gas gives you CH3Cl gas plus HCl gas. Now, I'm going to be honest with you. I'm not going to put one this tough on the test, but we're still going to take a look at it. And for this value here, we got a minus 363.22 kilojoules. Okay, so we got to take these 5 reactions and put them together into an energy level diagram. So where do we start? Well, let's take a look at the amounts here, the amounts of energy. Do you see that this is 74 without regard to sign, 103 without regard to sign, 92 without regard to sign, 242 without regard to sign, and 363 without regard to sign. I always like to start my energy level diagram with the reaction that has the biggest change in energy. So it's this one. So let's start writing that energy level diagram with that one first. So what I'm going to do is I'm going to take my piece of paper here and I'm going to draw this one so it looks like this. Now, why am I drawing an arrow down when it's minus 363.22? The answer is because it's negative. Okay, what am I going to put at the bottom of my arrow, the pointy part of my arrow? I'm going to put CH3Cl gas and HCl gas. What am I going to put at the other end of my arrow? I'm going to put CH4 gas plus 2Cl gas. Oops, this should be HCl gas. I made a mistake there. And this is minus 363.22 kilojoules going from here to here. So let's start incorporating the other equations that we need here. Well, look at this. I have this equation right here, this 2Cl and Cl2, and that seems to be that I'm going to make 2Cl gas right there. But I have a positive arrow. So what I'm going to have to do here is I'm going to move this over here like this. I'm going to do this, and that's positive 242.6 kilojoules, and I'm making my 2Cl gas. What do I start with? Cl2 gas. So now I've tied in 2 of my equations together. So I'm going to move this on up and I'm going to see what more I can do. Let's see. This one here where we have H2 gas and 1/2 Cl2 gas, I'm thinking to myself, how am I going to fit this one? And I'm not sure. So I'm just going to pass on that one for now, and I'm going to go to this one. So here I have carbon, H2 gas, and 1/2 Cl2 gas. Nothing really seems to fit, so I'm going to pass on that one. But I'm going to go to this one right here, where I have this H2 gas and the CH4, because I have this CH4 here. Now, here's something that we have to understand about this energy level diagram is that at every level, we should have the same elements for conservation of matter. I've got 1 carbon here, 2 chlorines, and 4 hydrogens. 1 carbon, 2 chlorines, and 4 hydrogens. No carbons and no hydrogens, but I have 2 chlorines. So I'm missing a carbon and 4 hydrogens. Well, doesn't it make sense to put CH4 gas here? Now, why is that? Well, to go from CH4 gas to CH4 gas takes no energy, so I don't have to change this number. And now this is looking better. And now I think I can incorporate this into my reaction. So I want to make CH4 gas, I think right here as my product. And I'm going to make it from carbon and hydrogen. And I need to make an arrow that allows this to be a product, but it's a negative arrow. So I'm going to do this. Boom. Now this one should be a lot shorter because it's minus 74, minus 74.87 kilojoules. And I'm going to write carbon solid plus 2H2 gas right there. So now I've connected this guy. I'm going to circle the little check mark. I've connected this guy, and I've connected these 3 together. I just need to incorporate those last 2. So what am I going to do here? I'm thinking to myself, I want to draw, well, I guess I'll take a shot at this one here. The 1/2 H2 and the 1/2 Cl2. Now, let's take a look at this one here. Do you see how this one is not complete? It's not complete because the carbon and the hydrogen make CH4. Where's the Cl2? Well, I have to put it over here too, so that I have 1 carbon, 4 hydrogens, and 2 chlorines at every step. So now let's incorporate this one here. So our product is going to be HCl, but our reactant is going to be 1/2 Cl2. So I'm going to go like this, starting here because that's a reactant. Because that's negative, I'm going to go down negative 92. And I'm going to end down here with what? Well, 1/2 Cl2 plus 1/2 hydrogen becomes HCl gas. Now, if we take a look at this, I have Cl2, but I've only used 1/2. So that means I still have another 1/2 Cl2 unused. And here I have 1/2 of a hydrogen, but I have 2, so I have 1.5 hydrogens left over. And I didn't use the carbon at all, so I've got the carbon solid. So now I've incorporated this guy into my energy level diagram. So the last thing to do is incorporate this last one, this 103. And I got to tell you, it looks like I got a carbon here. I've got 1.5 hydrogens here, and I have 1/2 chlorine here. That's going to make me this guy right here. Plus I have this HCl, which is there. So this is negative 103.18 kilojoules. And this shows how all of these are interconnected. If you add up all of these values, taking into account the negative and the positive, they will get you this value here. So, did you get it? Probably not, and it's okay. But here, again, are the things you need to take home. If you draw a reaction like this, what goes at the pointy part of the arrow? Product. What goes at the other end of the arrow? Reactant. If the arrow is up, it's because the reaction is endothermic. If you have an arrow down, it's exothermic. And what do you put at the pointy end of the arrow? Product. What do you always put at the pointy end of the arrow? Product. And what do you always put at the other end? Reactant. And so if we draw a reaction like this, H2O gas and H2O liquid, and I draw an arrow going up like that, that's endothermic, so it has to be positive. Happens to be 44.00 kilojoules. So if I draw an arrow going down over here, what does that value have to be? And the answer is, since it's the exact same reaction but reversed, it's negative 44.00 kilojoules. And this is another representation of our, if you will, the conservation of energy. Okay, there will be an energy level diagram on your exam, less like this one and more like the one I did with water. Okay, so let's see if we want to do one more, or actually it's 7:18, so I think I'm going to call it quits. And tomorrow we'll probably do some of this stuff right here. We'll do some more energy level diagrams also. Thank you for watching.